Welcome back to the deep dive. I want to start today with a bit of a challenge for you.
Okay, I'm ready. Lay it on me.
Imagine I hand you a book. It's a classic, maybe, I don't know, something you know really well. But I've done something terrible to it. I've taken a black Sharpie and I have redacted every single word.
Yeah.
You can't see Harry Potter, you can't see Sherlock Holmes, you can't see the or and. It is just page after page of black bars.
Okay. That sounds like a very boring or maybe a very censorship-heavy reading experience.
Stick with me here. Now, imagine that above every single one of those black bars, I've written a tiny little tag, a grammatical label. So
Yeah.
where Harry used to be, it says noun. Above Rand, it says verb.
Ah, okay. I see the picture.
My challenge to you is this. I want you to read through that book looking only at those tags. I want you to diagram the sentences. I want you to tell me exactly how the grammar flows, where the phrases begin and end, the whole structure, without knowing a single word.
That is... Wow. That's incredibly difficult. It sounds like a linguist's nightmare. You're stripping away all the meaning.
It feels impossible, right?
Yeah.
I mean, if I don't know the words, how do I know how they relate? But today, we're diving into a fascinating paper that claims computers can do exactly that.
Yeah.
And they don't do it by guessing. They do it by looking at the physical shape, the geometry of the sentence structure.
It's a really cool concept. We're looking at a paper titled Tree Topological Features in Classifier-Based Unlexicalized Parsing.
Which, let's be honest, is a bit of a mouthful. I feel like I need a glossary just for the title.
It is a dense title. It's by Samuel Chan, Mickey Chong, and Lawrence Chung from the Chinese University of Hong Kong. And, you know, essentially they're arguing that syntax, the way we build sentences, has a kind of fingerprint, a geometric shape.
A shape.
Yeah, and if you can measure that shape, you don't actually need a dictionary to understand the grammar.
It's almost like identifying a tree by its silhouette against the sky at dusk, instead of, walking up and looking at the veins on the leaves.
That is a perfect analogy. Like, it's a move away from semantics, so the meaning of words, and into the realm of topology.
Topology, right.
Yeah, and topology is just the study of geometric properties that are preserved even when you stretch or twist things. They're basically asking, does the shape of the branches tell us what kind of tree we're looking at?
Okay, so before we get into the how, and I should warn you, there is some really interesting math coming up. Let's unpack the problem they're trying to solve. The paper talks about unlexicalized parsing. We need to translate that.
We do. It sounds like something you'd get treated for at a hospital. I'm sorry, you've been diagnosed with unlexicalized parsing.
Exactly.
No, so parsing is just the process of breaking a sentence down into its grammatical parts. It's sentence diagramming, like you might have done in middle school.
Okay, yeah, I remember that.
Yeah.
Drawing the lines.
Right. Now, when we say unlexicalized, we mean the computer system, the parser. It doesn't see lexical tokens. It doesn't see the words apple, run, democracy, or blue.
So it's flying blind.
In a sense, yeah. It only sees the tags. It sees N for noun, VB for verb, DT for determiner. And the authors point out right away that this is usually a massive disadvantage because words carry clues.
Right, context. If I see the word devoured, I know a noun is probably coming next, and it's probably something edible, like sandwich. It's not going to be devoured the concept of ennui. Well, I mean, maybe poetically, but usually not.
That's the semantic clue. But if you only see the tag verb, it's ambiguous. It could be slept, which doesn't take an object, or it could be gave, which takes two objects. Without the word, you lose that blueprint.
And the paper highlights a specific issue with what they call heaviness, right?
Yes.
Where the blind parser usually crashes.
Yes. This is kind of the Achilles heel of traditional unlexicalized parsers. They just match tags. But a tag is a great equalizer, and not in a good way. The tag NP noun phrase looks the same whether it's a simple word like he or a massive complex phrase like the big red dog that chased the car down the street.
So to the computer, he and that 20-word description are just NP. They're the same data point.
Effectively, yes. If you're just matching tags, they're identical. But linguistically, they behave very differently. A huge, heavy noun phrase changes the balance of a sentence. It changes where you can put it. And if your parser ignores that heaviness or that internal complexity, it's going to make mistakes. It's going to group things wrong.
So this is the mission of this deep dive. The researchers, they wanted to find a way to let the computer see that complexity, that heaviness, without cheating and looking at the words.
That's the goal. They wanted to prove that the structure itself carries information.
And the solution they came up with is these tree topological features, or TTFs.
TTS.
Sounds like a specialized tool you'd buy at a hardware store. Hand me the TTFs. But it's really about geometry. They propose that instead of just reading the tag, the system should measure the subtree.
Right. Think of that sentence diagram again. It's a tree structure. S for sentence at the top, branching down into phrases, and then finally the leaves at the bottom, which are the tags. The researchers argue that we can measure the topology of these branches. Is the branch heavy? Is it flat? Does it lean to the left or the right?
Now, I have to ask the skeptic's question here. Why do this without words? I mean, if we have the words, why tie one hand behind our back? Is this just an academic exercise?
It's partly to prove a theoretical point, yeah. They wanted to minimize interference. If they let the computer see the words, they wouldn't know if the improvement came from the shape analysis or just from, knowing the dictionary definitions. But there's a very real practical side. If you don't need a massive dictionary of word definitions, your system is much lighter and faster.
So it's leaner.
Much leaner. You don't need a database of 1 million words,
Yeah.
just the grammar tags.
Okay, I'm sold on the utility. Let's get into the toolkit. The paper proposes 4 main categories of these topological features. The 4 pillars of tree topology, if you will.
Let's walk through them.
Pillar number 1 is node coordinates.
Right. This is effectively the GPS of the sentence tree.
Okay, GPS implies a grid. How do we map a sentence on a grid? I mean, it's just a line of text.
Well, the tree gives it verticality. Node coordinates, or NCs, locate the root of a specific subtree. They use 2 metrics here. First, the level of focus.
Level of focus.
Yeah, imagine the tree has layers, the individual tags at the bottom. The leaves are level 0. The phrase right above them is level 1, and so on up to the whole sentence at the top. The level of focus just asks, how high up the ladder are we?
So are we dealing with a tiny twig near the bottom, like a single adjective, or a main branch near the top, like the main subject?
Precisely. And the second metric in this GPS is relative position. Where does this node sit horizontally? Is it at the beginning, the middle, or the end of the sentence?
That seems almost too simple to be useful. It's at the beginning, so what?
Well, think about English structure. Position dictates function. A noun phrase at the very start of a sentence is almost always the subject. A noun phrase after the verb is the object. So just knowing I have a high-level node at the far left gives the computer a massive probability clue that it's looking at the subject of the sentence.
Okay, that makes sense. It gives the parser a sense of place. It's context without content. Okay, let's move to pillar number 2. This one feels very intuitive to me. The span ratio.
Yes, the SR. This relates back to that concept of heaviness we touched on with the big red dog.
Heaviness. I like that term for grammar. It feels substantial.
It's a measure of coverage. The span ratio asks, how much of the total sentence does this specific phrase cover? You calculate it by taking the number of terminal nodes, the bottom tags covered by this phrase, and dividing by the total length of the sentence.
So let's do the math to make this concrete. If I have a 10-word sentence and one phrase covers 9 of those words,
Then the span ratio is 0.9. It's huge. It's a heavyweight phrase.
and if it's just the word the,
Then it's 0.1. Tiny. If the span ratio is close to 1, that node covers almost everything and is likely the very top of the tree. This is the computer's way of weighing the phrase.
right.
A simple pronoun has a tiny span. A complex description has a huge span.
It's giving the sentence physical weight. I can visualize that. Okay, pillar number 3, aspect ratio. This sounds like we're talking about my TV screen settings.
It's actually similar geometry. The aspect ratio, or AR, measures the shape of the subtree itself. It's the ratio of non-terminal nodes, the grammar tags like NP, VP to the terminal nodes.
Break that down. What does that actually tell us about the shape?
It tells us about the flatness or the branching factor of the tree. So imagine a bush versus a pine tree. A bushy or flat tree has one parent node with a dozen children nodes directly under it.
Okay, so wide and short.
Right. That has a distinct ratio. A pine tree is tall and skinny. Every node only has 1 or 2 children going down and down and down.
Different grammatical phrases have different shapes.
They do. The researchers found that different types of phrases tend to have consistent aspect ratios. So if the computer sees a certain ratio, it can statistically guess, hey, this is really flat. This looks like the shape of a coordinate phrase.
It's like a silhouette.
It is. It's geometry as identity.
That leads us to the 4th and final pillar, which I found the most technically interesting, the skewness measure.
The SM. This is where we determine if the tree leans.
Leans, like the Tower of Pisa.
In a way, yeah. The researchers developed a formula to calculate whether the weight of the subtree is distributed to the left or to the right.
How do they calculate that without putting the sentence on a physical scale?
They use a pivot. Imagine looking at a phrase. They find the middle word, the median tag. That's the pivot point, like the fulcrum of a seesaw.
Okay, I'm visualizing the seesaw.
Then they measure the path lengths from the top node down to all the other words. Words to the left of the pivot get a positive distance. Words to the right get a negative distance. They crunch these numbers to get a skewness measure.
So if the tree is perfectly symmetrical, the skewness is 0. The seesaw is balanced.
Theoretically, yes. But here's where it gets really interesting linguistically. The researchers note that English is generally a right-branching language.
Right branching, that means we add stuff to the right.
Yes. In English, we usually put the main item, the head first, and the modifiers follow. We say, the dog that barked, the man who knew too much. The description trails off to the right.
As opposed to some languages where you put all the description first and the main word last.
Correct. So in English, as you go higher up the tree structure, say from level 2 to level 5, the skewness value typically becomes more and more negative.
Negative?
Yes, because the right side is heavier, and in their formula, the right side carries the negative value. A negative skewness measure means the complexity is hanging off the right side. This is a massive clue for the parser.
Yeah.
If it sees a structure that is leaning heavily left, like a negative image of what it expects, it might question if it's analyzing the sentence correctly. It's a reality check based on the physics of the language.
It's amazing that you can reduce grammar to a negative number.
It's the physics of language.
And that's a perfect transition. I want to connect this math back to the actual physics of grammar section of the paper, because the researchers didn't just invent these metrics for fun.
No, not at all. They're trying to capture things linguists have known for decades, but never really quantified for a computer this way.
One of the big examples they give is the heavy NP shift.
Yes. This is a classic example of how size matters in word order.
Give us an example of this shift in action, because I think we do this subconsciously all the time.
We do. Okay, so standard English word order is subject, verb, object, indirect object. So you might say, I gave to Bill the books. That's standard.
Okay.
But what if the books isn't just the books?
What if it's the books that my friend bought yesterday from the rare bookstore in London?
Exactly. That is a heavy noun phrase. If you try to jam that in the middle, it sounds awful. Listen to this. I gave the books that my friend bought yesterday from the rare bookstore in London to Bill.
Yeah, that's terrible. By the time you get to Bill, you've forgotten what the sentence was even about. It's clunky.
It creates a memory bottleneck for the listener. So, subconsciously, humans shift it. We move the heavy item to the back. We say, I gave to Bill the books that my friend bought.
We save the heavy lifting for the end.
And the span ratio we talked about earlier, it directly measures that weight. The parser can predict this word order shift because it sees the high span ratio. It expects the heavy item to be at the end.
It's using geometry to predict grammar.
That's it.
That is so cool. There's another linguistic concept they tackled, which they call the bread and butter problem. Coordination.
Yes. And. The word and. It is the bane of parsing.
Why is and so hard? It's 3 letters.
Because it creates ambiguity of scope. If I say, I like dogs and cats with hats, do I like dogs and cats with hats, or do I like dogs and cats, both of which have hats?
I see. Does the hat apply to just the cat or the dog too?
Right. A computer hates that. But humans usually figure it out because we prefer parallelism. We like balanced structures. We want the things on both sides of the and to be similar.
So the researchers found this balance in the numbers.
They did. They looked at coordinate structures, phrases joined by and found they have significantly different aspect ratios and skewness measures compared to non-conjoined phrases.
How so?
They're more symmetrical.
So the parser looks at the math and says, hey, these 2 distinct branches have the same geometric fingerprint. They probably belong together.
It's finding the rhythm of the sentence through numbers.
So we have the theory, we have the metrics, we have the linguistic justification. Now we have to talk about the experiment. How do they actually build this thing?
They used a method called the chunk and merge approach.
It sounds a bit like a cookie recipe. Chunk and merge.
Ideally, it's less messy than baking. It's a bottom-up process. Imagine the computer scanning the string of tags, noun, verb, determiner, noun. It stops at every gap between them. At every gap, it have to make a binary decision. Do I chunk, meaning I separate these two, or do I merge, meaning I combine them under a parent node.
So it's stitching the sentence together from the bottom up, decision by
Right,
decision.
step by step. But to make those decisions, it needs a brain. And for that, they used machine learning. Specifically, something called ensemble learning with the AdaBoost algorithm.
I'm a boost. I've heard that term.
So it's a classic machine learning algorithm. Think of it like a committee. Instead of trying to create one super genius rule that understands all of English grammar perfectly, which is impossible, AdaBoost creates a committee of weak learners.
Weak learners. That doesn't sound very promising.
It sounds counterintuitive, I know. Imagine a committee of people who aren't very smart.
Huh?
One guy only knows about verbs. He's right maybe 60% of the time, but only about verbs.
Mm-hmm.
Another person focuses on the end of sentences. She's right 55% of the time.
So individually, they aren't great. They're barely better than a coin flip.
Individually, yeah. But if you combine hundreds of them and you weight their votes based on who is usually right in the situation, you get a strong learner. You get the wisdom of the crowd.
So we are trusting a mob of idiots, but a well-managed mob.
A statistically weighted mob. And it turns out the mob is very smart.
So they took this chunk and merge parser, powered by this AdaBoost committee, and they fed us the Penn Tree Bank, which is the gold standard data set for this stuff. How did it do?
This is the big reveal. First, they established a baseline. Using just the tags, no geometric features, the parser had an F-score, which is a measure of accuracy, of 78.28%.
78%. Decent, passing grade in school, but not exactly something I'd want translating my medical documents.
Right. Then they started adding the topological features. And adding any single one of the 4 features, just skewness or just span ratio, it improved the score significantly.
So every angle of geometry helped.
Every single one. But the winner was model P6. This was the model that combined all 4 features: coordinates, span, aspect, and skewness. Yeah.
And the score.
It achieved an F-score of 84.03%.
That's a huge jump in this field. 6 percentage points is the difference between a toy and a tool in AI.
It is. But here is the real kicker. This unlexicalized parser, remember, it knows 0 words, it has no dictionary, it matched the performance of the famous early lexicalized parsers.
You're talking about Majorman's parser from 1995.
Exactly. Majorman's parser was state-of-the-art. It used the meanings of words. It knew bank was a noun and what it meant. This system, just by looking at the shape of the tree, performed just as well.
That is wild. It's like understanding a conversation just by watching the hand gestures and the rhythm, without hearing the words.
That's a great analogy. It proves that syntax is structurally redundant. The shape carries the meaning, or at least the structural intent, almost as much as the words do.
So what does this all mean for us? Why does this matter beyond just being a cool party trick for a computer?
Well, aside from the theoretical coolness, there are 2 big takeaways: efficiency and disambiguation.
Let's start with efficiency. We touched on this, but how big of a difference is it?
Computing power is finite. Traditional parsers that rely on lexicalization, they need massive databases. They need to know every word in the language and its potential roles. That's heavy.
Right. And if you encounter a new word or a made-up word slang, a brand name, a traditional parser might just choke.
Exactly. If I say I Googled it, and the parser doesn't know Google can be a verb, it fails. But this topological parser, it doesn't care. It just sees the tag. And the math for skewness or span ratio is simple arithmetic. It's lightweight and fast.
That makes it perfect for things like mobile devices or real-time translation where you don't have infinite memory or battery life.
Precisely. It allows for parsing on the edge.
Yeah. And then there's disambiguation. This is where the geometry really shines. The paper gives a specific example.
This was the by versus as example.
Right. Compare by buying big blocks of stock versus as UEL stop trading.
Okay, let's look at those. By buying is a prepositional phrase. As UAL stopped is a subordinate clause.
To a human, those are totally different. But to a simple tag matcher.
They look confusingly similar. You have a small connector word followed by a complex phrase, but the shape of the trees underneath those phrases is different.
Because a clause has a subject and a verb inside it, so it branches differently.
Yes. The fingerprint of a prepositional phrase has different means and standard deviations in aspect ratio and skewness than a subordinate clause does. The computer looks at the shape and says, this one is too pointy to be a clause. It must be a prepositional phrase.
It's profiling the sentence.
It is. It's distinguishing them by their geometric signature.
It really changes how you think about language. We usually think of it as this ethereal, creative thing, poetry, emotion. But this suggests it's also rigid geometry. It has physical laws.
It connects linguistics back to the natural world. Symmetry, balance, center of gravity. These aren't just architectural terms, they're grammatical terms.
So we've covered the blind parser, the four pillars of geometry, the physics of heaviness, and the impressive results. As we wrap up this deep dive, what is the one big thought you want our listener to walk away with?
For me, it raises a question about the human brain. We've proven here that a computer can achieve near-human parsing accuracy just by looking at geometry without knowing what any of the words mean.
Right. It works.
So it forces us to ask, is this how we do it? When you hear a sentence, are you actually processing the definitions of every single word in real time? Or is your brain, at a fundamental level, a geometry engine?
That's a fascinating thought. Are we just instantly recognizing the shape of what's being said, the balance, the skewness, and filling in the meaning later?
Are we listening to the melody or the lyrics? Maybe syntax is more about structural balance than we ever realized. Maybe we are all just subconscious geometers.
That is a thought that is going to keep me up tonight. I'll never look at a sentence the same way again. I'm going to be looking for the pivot point.
Always check the skewness.
Always check the skewness. Thanks for listening to The Deep Dive. We'll catch you on the next one.